Faults are important components of all sedimentary basins, but they're not simple knife-edge cuts that just offset strata. They process their wall rocks. Traditionally, structural geologists worked at outcrop, particularly in ancient mountain belts, and in these situations the fault rocks and fault zones have formed in fully lithified materials. Well, in sedimentary basins, that's not the case. We're dealing with rocks that are not fully lithified. So let's go and look at the types of materials that we find in these situations. We're going to look at different types of starting material: clean sandstones, impure sandstones, and then clay layers that tend to smear out. We'll look briefly about what their permeability characteristics are, and then we'll go and look at carbonates, where mineralization is important. And I'll just say a few words at the end about upscaling. So let's start off with fault rocks in clean siliciclastic successions, such as these Aeolian sandstones on the Moray coast of Scotland. So in these situations, where the rocks perhaps are not fully lithified, the original sandstone will contain significant porosity. And under low confining pressures, in other words, where these rocks have not yet been deeply buried, if we fault this succession, the grains will pull apart. In other words, the rock will dilate, increasing the porosity and therefore enhancing the fluid transmissibility of this particular part of the succession, the fault rock. Here an example from Sicily of a very weakly buried sandstone. And here in thin section we can see the enhanced porosity that's been picked out by that black staining, which is iron mineralization, which is preferentially developed within the disaggregated porosity of the little fault zone. Well, in more deeply buried situations, cataclasis occurs, where the grains, rather than just simply disaggregate, break. This reduces grain size, reduces the sorting of the original rock, and with grain repacking effectively reduces the porosity within our small fault zone. There's an additional component to this, which is that these zones of microfaulting, they're called deformation bands, are preferentially cemented as well. And this is because quartz cements are preferentially precipitated onto the broken grain edges rather than the original sedimentary grain boundaries. So cataclasis has reduced the porosity by grain size reduction, the grains have been repacked, and any quartz cementation that occurs is preferentially developed onto the broken edges of the cataclasite. So these little microfaults become zones of preferential cementation, which further reduces the fluid transmissibility. So these are clean, porous sandstones. What about impure sandstones, which consist of quartz and phyllosilicates, that's clays or detrital mica? Well, in our cataclastic zone in here, the phyllosilicates can act as semi-rigid bodies and rotate into preferred orientation parallel to the little microfault zone. Let's just fade away the quartz grains, bringing out the phyllosilicates. And here they are, creating this framework of aligned phyllosilicates. So this creates a so-called phyllosilicate framework fault rock, PFFR. And we can see if we just cartoon up some fluid across this. And these, along with the cataclasis of the quartz grains, will further reduce the fluid transmissibility across the fault zone. Now let's look at a sandstone shale sequence here, and let's just look carefully at the different behaviours of these two layers. The sandstone has faulted, but look what's happened if we trace the lamination out in the siltstone claystone above. This so-called shale is sheared rather than faulted, so has behaved in a ductile fashion compared to the brittle localised faulting in the sandstone. This is clay or shale smear. So we've got different behaviours depending on the original material: clean sandstones, impure sandstones, and then shale or claystone layers. Clean sandstones, when they've never been deeply buried, can disaggregate, or they can break in cataclasis to make different types of microfault zone. Impure sandstones, those clay or detrital mica sheets, can become aligned in the fault zone to make a phyllosilicate framework fault rock, PFFR. The claystone or shale layer can become smeared out into the fault zone. So how do these different types of fault rock impact on fault zone permeability? Well, there was a classic study reported by Quentin Fisher and Rob Knipe from 2001, and they'd collected data from samples from wells from the North Sea and Norwegian basin. Most of these materials were Jurassic rocks. So for clean sandstones that had not been deeply buried, they tended to make disaggregation seams with those really high permeabilities. Where these rocks were more deeply buried, rather than disaggregate, the fault zones showed grain cataclasis, and these have got a reduced permeability. And finally, really deeply buried rocks from the Reutlingen with the cataclasites there have got really low permeabilities. So as the pre-faulting depth of these materials increases, then the fault rocks show radically reducing permeabilities. Where sandstones had not been deeply buried before faulting, their fault rocks have very high permeabilities. Where the sandstones had been significantly buried before faulting, then their cataclasites show very reduced permeabilities. What about clay smear? Well, that plot's right over here with, as you might expect, low permeabilities as well. But it's interesting that the cataclasites, the deeply buried sandstones, have similar permeabilities to the clay smears. What now about the impure sandstones? Well, they plot here. This is the phyllosilicate framework fault rocks, sort of halfway between the clay smears and the cataclasites of the clean sandstones. The range in permeability of the phyllosilicate framework fault rocks relates to the burial depth of the fault zones. Compare that with the clean sandstones. They too show radically decreasing permeability with depth. Let's just look now at another set of sandstones. These come from New Zealand, and here we have these microfaults, the deformation bands, developed within the sandstones. If we look quite carefully at these, we find the deformation bands consist not only of broken grains, because this sandstone contained lithic clasts that have been altered diagenetically into balls of effectively fine-grained clay, which means when they fault, these degraded clasts are smeared out into the deformation band, into the microfault zone. So we have this micro clay smear of the grains. So we're getting another type of phyllosilicate framework fault rock in these situations. Let's move on now and look at carbonates. Carbonates tend to lithify very close to the Earth's surface, even at the Earth's surface in some cases, which means that the sedimentary grains tend not to disaggregate, and cataclasis is a really important process within carbonate fault rocks. But so too are cements. Let's look at an example here from the north coast of Scotland, where dollar stones have been faulted. That cliff is a fault scarp, and we zoom in and have a look at it, we can see complex cataclasis and grain breaking, but also quite complicated cement histories picked out by those different colours. So mineralisation in the fault zone is a really big deal. Shallow level fault zones, such as this one in the Jura, where the fault probably developed within a kilometre of the Earth's surface, cementation is less important here, and we have an intense vuggy fracture porosity that is on the fault zone. So this is a highly porous fault rock. So let's go and have a look at this example from the Lower Jurassic of South Wales, where we've got thin limestone bands and carbonate mud rocks that separate them into a multi-layer. And the faulting in this has generated a fault zone coming down across the cliff. If we just zoom in on this, we can see that the fractures are filled with calcite mineralisation. Another example of synkinematic mineralization. Here we're looking onto another fault plane from the French Alps, where synkinematic mineralization is manifest by these shear fibers, fibrous growth of new calcite on the fault plane, precipitated in cavities as the fault plane slipped. You can see more about these processes and other examples in other videos on this channel. So fault rocks in sedimentary basins is not just simply about the structural geology. Diagenesis is also fundamentally important, controlling mineralization in fracture porosity, as we've just seen in the carbonates, for grain cements, particularly on the broken grains that we saw in the quartz sandstones, and for preconditioning weak grains through essentially rotting of feldspars and lithic fragments into balls of clay that then can get entrained into the fault zone. So a quick look at the range of different fault rocks in sedimentary basins. But these can be really heterogeneous. The question then is, if we want to predict the behaviour of faults and their ability to transmit or impede fluid flow through sedimentary successions, can we go upscale to predict the different types of fault rocks for different parts of faults through sedimentary successions? Well, that's a topic for another video.